Greetings. Welcome to my series on AP Physics C, Electricity and Magnetism, where I'll be covering electric flux and Gauss's law in this video. Now, Gauss's law is a really handy equation that admittedly looks a little frightening at first glance. My goal is to help you build intuition for how and why it works, and show you how to make the application of it as simple as humanly possible. So, here we go. And my first question to you is, what's in the box? I mean, take a really good look. Yeah, I mean this box right here. If you can't really tell, I don't really blame you. It's a little hard to tell without at least something to give you some kind of information about it. So I'll give you another box. Okay, so how about this one? Can you tell now? The first thing that should immediately be apparent is that the box is glowing mysteriously. The light appears to be coming out of the surface on all sides, so you could maybe deduce that there must be a light source inside of the box. Maybe a light bulb, maybe a big LED, maybe a trapped pixie, who knows? Whatever the case, the light rays coming out of the box indicate that a light source must be inside. Now, if I give you this other box, which is also glowing, let's suppose that there is in fact a light source inside of both of these boxes. Then, could you tell me which one has the more intense light source? If you said the rightmost one, I'd be inclined to agree with you. There seems to be more light coming out of this box overall compared to the other two, so the light source producing said light must be emitting more rays overall. Now, the point of this silly little game is to acknowledge that seeing the rays of light coming out of the box gives you information about what's inside. You can tell that there's a light source of some kind inside, and you can tell how intense that light source is by how much light is coming out of the box. All of that plays into the concept of flux and how it relates to Gauss's law. Flux, as a quantity in physics, is the measure of the flow of some physical quantity or vectors through a surface area. As shown from the boxes, this certainly applies to light rays, so let's take a look at another hypothetical. Say we've got a house with two equally sized windows, and the sun is beaming down onto the house from overhead. First, should we say that the roof window or the wall window has more of the sun's rays passing through it? Take a second to think about it, pause if you need to, but if we think about which window is more directly facing the sun, the rooftop window, intuitively, should have more sunlight coming directly through. The incident angle is more head-on, so there's less surface facing away from the sun itself. Next, suppose we decrease the size of either window. What happens to the light passing through now? Well, now there's simply less transparent area for the sun's rays to pass through. So what we considered to be the window is smaller overall, and less light is able to pass through, so logically, less light will pass through. Finally, say a cloud passes overhead that partially blocks the sun. Again, what happens to the amount of light passing through the window? Well, here, it's not necessarily that the receiving end is smaller, but the number of rays from the sun has just directly decreased. Because of this, it's safe to assume that fewer light rays will make it to the window, so again, less light will come in. From all of that, we can say at least three things that should affect the flux of particles, lines, or vectors through a surface. First is the angle at which a vector hits a surface or exits from it. This animation here does a pretty neat job of animating it. Note that the more parallel the surface of this orange plane is to the path the particles are taking, the fewer particles are able to pass through the surface itself. The more perpendicular it is, the more particles will impact it head-on. The next thing that affects flux is the surface area of the surface. This one should feel fairly intuitive, just from looking at the animation. The bigger the plane, the more area there is for particles to hit. The smaller the plane, the less area there is in the path of the particles. Makes sense. Finally, the density or intensity of things reaching the surface also affects the flux of those things through a surface. Even if the surface is doing everything right, it's huge and it's perpendicular to the particles, well, if there are very few to no particles actually present, then the through traffic is going to be really low. If there are a ton of particles passing through, like you're starting to see here, then the flow through the surface should naturally increase. Makes sense. Tying all this into electrostatics, we say that when an electric field passes through a certain surface, there's an electric flux associated with these three variables. Electric flux is the first major component to Gauss's law. And by the way, if you want to play around with some of these animations a little bit more, I linked the website where I found them in the description. So electric flux, denoted by capital Phi, is the product of the perpendicular component of electric field strength, E, with the area of the surface that it's passing through. Now, there are a number of ways to calculate it, all taking influence from those three variables mentioned before. Flux, first and foremost, is a dot product. Dot products are best used when something is maximized when two things are aligned, and minimized when two things are perpendicular. Now, that might strike you as odd, seeing as we just established flux should be maximized when the surface is perpendicular to the flow. But there's a very good reason for this that we'll get to momentarily. Now, our dot product can be calculated more directly by multiplying the magnitudes of E and A with the cosine of the angle between them. And finally, we could just say that any component of the electric field that's perpendicular to the surface area will give you flux just as well. Now, one interesting thing with this equation is that we have to agree on how to turn a two-dimensional surface into a vector that's represented by an arrow. To do that, we say that its magnitude is the total surface area and how you normally calculate it, like length times width, but its direction will be indicated by an arrow perpendicular to the surface. In equation form, it looks like this, where the scalar multiplier is the surface area and the direction is adopted by this unit vector, n hat, which is perpendicular to the surface at all points. You can treat this kind of like you did with normal force back in mechanics, always perpendicular to any surface that it's present on. This means that when an electric field vector and our normal vector are parallel, such that the angle between them is 0, the electric flux will be at a maximum. That's why we represent this as a dot product. It's maximized when the angle between the two main vectors is 0. And if you're having trouble kind of coming to terms with that, or like if you're having trouble seeing it, like when a problem is presented to you, when in doubt, always just draw a picture or take advantage of any picture you are given. Visualizing these things is really key to helping to understand them a little better. Now, while that handles the flux for a singular vector, what we really care about is the total electric flux through the surface due to all vectors passing through it. You can think of the total electric flux as the number of field lines that are passing out of or into a surface. The total amount, one way or another, makes the net flux. To establish a sign convention for this, let's say that field lines passing out of a surface contribute to positive flux, and field lines passing into a surface contribute negative flux. To get a feel for things, let's take a look at a visualization of this idea. This picture here shows the flow of electric field lines from a positive charge to a negative charge. It's worth noting that this depiction takes some artistic liberties. Electric field, as of right now, is a static thing. It does not actually move from one place to another. And electric field is also continuous. There's no discrete countable number of electric field lines in space. This animation simply serves to make our lives a little bit easier in visualizing how flux works, so don't go too crazy. Now, to test the flux through a region, we need to create an imaginary closed surface somewhere to actually have a flux to pass through. I'm going to create one around this positive charge first, this green line here. My challenge for you is to think about what the net flux is through each surface that I'm going to create and why. And to do this, focus on counting how many lines are going out of the surface and how many lines are going in. Add them up, and then find the total difference between the two. Now, there's our first line, and next, I'm going to place a surface around both the positive and negative charges. Again, try counting the number of lines going out versus the number going in. Does one outweigh the other? Finally, I'll place a third surface in a rather strange spot, just out in the open space, not enclosing any charges at all. Here, there are still lines passing into and out of it, so think about what the total flux is with that. Now, if you've paused and thought about it a little bit, here I'm going to go ahead and let the cat out of the bag a little bit. So first, we'll start with the green line. The total flux through the green surface is net positive. You'll notice that the whole way around, there isn't a single line that's entering the surface. All are being exported elsewhere. None are entering. The net flux through the white surface, on the other hand, is 0. It helps to follow the lines that are exiting the surface all the way to their termination point. Any outward lines from the positive charge re-enter the surface later on near the negative charge, so they all cancel themselves out. Finally, the pink surface also has a net flux of 0. This one is a bit easier to count. There's only 4 lines total that are either entering or exiting. 2 lines are seen entering the surface to the top right, and then those same 2 lines later on exit the surface at the bottom right. Thus, the total positive flux cancels out with an equal and opposite amount of negative flux, and so the total net is 0. Now, it's important to note that electric field is continuous. We can't really count lines like this when it comes to actually calculating the real net flux through a surface. To do that, we'll have to resort to slightly more continuous methods, and that's where we're heading next. So one way to do that is by estimating a tiny amount of flux coming out of a tiny division of the total area of a surface, like you see on the image over here. This tiny flux is called d phi, and the tiny area is called dA, like you see on the image. Setting that up as an expression, we can say that d phi is equal to E times the tiny surface area, dA, times the cosine of the angle between them. So really just the standard flux equation, but really tiny. Now, that's only a small part of the total area. So the next step is to calculate this value for each small division all the way around the surface, and then add them all up. If that sounds like doing an integral, you'd be right. Kind of. Our net flux can be found through this equation right here. That is an integral, but it's a very special type of integral which must be evaluated through an equation representing the surface of the shape that you're using. This is known as a surface integral, and it's the main reason that most would probably say that Gauss's law looks quite scary. Now, here's the thing. Evaluating surface integrals is not only outside the scope of any calculus class you'd be taking in high school, but they're very much outside of the scope of this class as well. So why the heck are they popping up here? Well, the main reason is that this operation is quite important for the execution of Gauss's law, so it kind of has to be there. But the good news is, how we apply it relies on the result of many surface integrals that you already know. Many of the surface area formulas for basic geometric shapes like spheres and cylinders are the result of surface integrals. The surface integral through a sphere is 4 pi r squared, and through a cylinder, you'll get 2 pi r L, which is the length of the cylinder, plus 2 pi r squared, accounting for the caps on either end. It'll turn out later that really those formulas are all you need to handle this scary part of the equation. There's no vector calculus needed. So all of this brings us to Gauss's law officially. It's a statement that the net flux through a closed surface is proportional to the total charge enclosed by that surface. This harkens back not only to the lights inside the box at the very beginning of this video, but also to the surfaces being drawn around the charges from earlier in the video during that little GIF animation. If a surface is enclosing exclusively a positive charge, as seen here, the net flux through that surface will be outward overall, positive. If a surface encloses only negative charge, the net flux will be net inward, negative. If the surface encloses both a positive and a negative charge, both of equal magnitude, then the net flux will be 0, as all lines exiting will re-enter the surface later on, canceling themselves out. Now, the closed surfaces I'm referring to here are meant to fully enclose a region of space. In E&M, usually we'll call these Gaussian surfaces. Later on, in a later unit, we'll call these Ampérian loops when we get to magnetism. Another important detail is that charge must be enclosed in order for there to be a net flux. If charges are nearby, but not enclosed by the surface, they will still not really contribute to the net flux because any lines from those charges will again enter the surface and then later on exit the surface back again, canceling themselves out. So all of this leads to the following mathematical relation, known officially as Gauss's law, which is that the net flux given by the surface integral of E dot dA is equal to the total charge enclosed within the surface you create divided by epsilon naught, which again is the permittivity of free space, a constant. And again, this equation seems rather horrific to try and evaluate. But if we make a couple of really convenient assumptions, it simplifies this equation by a lot. So let me show you how we get to that version and why we can do it. So the simplified Gauss's law that you'll normally end up using for AP Physics C, at least, is the electric field strength times the surface area of your Gaussian surface equals the total charge enclosed divided by the permittivity of free space. And just as a reminder, the permittivity of free space is a constant which equals 8.85 times 10 to the negative 12 farads per meter. It's a number that is available on your AP Physics C formula sheet, so don't worry about memorizing it again. Now, the reason we can simplify Gauss's law to this state is because while it can be used in general with the scarier form, it's really only useful in very specific scenarios where it takes on the simpler form. So the conditions you'll need for that are that the electric field E be constant everywhere on the surface, or whatever surface you make. This is important because it will allow you to treat the electric field E as a constant, and thus you won't have to factor it into the surface integral part of the equation. This means your surface integral will really just become the surface area of whatever Gaussian surface you make. Next, another really great simplification is to choose a Gaussian surface that's radially symmetrical. That includes circle adjacent shapes like spheres and cylinders, where all points on the surface are equidistant from the center. So here, the main advice is to choose a Gaussian surface that's like that. Don't choose a Gaussian surface that's like a potato or like an amoeba or something. An example of that would be like this line of charge right here. A cylinder is a really great shape to enclose an infinite line of charge like this, because all the points on the side of the cylinder are equally distant from the line that's in the center of your surface. This is going to help ensure condition 1 as well, where we want the electric field strength to be constant at all points on the surface. Recall that by Coulomb's law, electric field falls off as opposed to like with r squared. And so the further away you get from a charge, the weaker or stronger the electric field is going to be. And you really don't want that with a surface that you're trying to keep uniform. Finally, it's important that the electric field be perpendicular to the surface at all points. This is so we don't have to worry about the cosine between E and A. If E is always perpendicular to A, then we can simply multiply them together without any angle shenanigans. So going back to the cylinder example, that also happens here. The electric field lines are going to be radiating outward away from the line of charge in the center. And thus, they're going to radiate out of the surface of the cylinder perpendicular to its surface at all points. That's ideal. So all in all, if you set it up correctly, Gauss's law is an extremely convenient tool to help evaluate electric field strength around solid uniform shapes like this one by making use of symmetry. Now, to show what that looks like, I'll run through a couple of examples just where it's extremely useful, and hopefully you'll get the gist of it from there. Let's take a look. So for this first example, we have just a standard positive point charge with a charge plus Q, and our goal is to determine the electric field strength E at a distance r from the charge. Now here again, we're going to note that the electric field lines from a charge like this are going to be radiating outward, kind of in a circle, or if you're thinking three-dimensionally, they're really going to be radiating outwards in a three-dimensional space, just radially. So again, to approach a problem like this with Gauss's law, it's helpful to start with Gauss's law itself, because this equation gives you the guideline for what things you need to look for. Now here, electric field is our goal, so it's okay to just leave that as is. But two things we need to figure out are the surface area of whatever surface we're going to make, as well as the charge that's enclosed within that surface. So to start, note that here, if we want to enclose all of the electric field lines that are coming out away from this charge, well, a sphere is honestly not a half bad option. Field lines are radiating in all directions, so a sphere is going to be able to capture all of those, and that's going to mean it's going to be a pretty solid Gaussian surface. Also, it's a sphere, so it's symmetrical, and the field lines are all going to hit the edge of the sphere at the same point, at the same distance away from the positive charge. So if that's going to be our surface, then the surface area of a sphere is 4 pi r squared. And so that pretty much knocks out the left side of this equation and what we need for it. Now, really the right side is also pretty trivial, because here, well, since we already know the charge of the point that's inside of our surface, the charge enclosed is really just the charge of this point. That means that we can really go ahead and just plug stuff in. We've got over here the electric field times the surface area of our sphere, which is 4 pi r squared, and that's going to equal positive Q divided by epsilon naught, which again is a constant that you have available. So then rearranging and solving for E, we end up with positive Q divided by 4 pi r squared times epsilon naught is going to be our electric field strength at any point along this sphere. Now, this equation should come as no surprise to you, although maybe you need it in a slightly different form, because this equation effectively is just the electric field form of Coulomb's law. If we rearrange it so that it's 1 over 4 pi epsilon naught times Q over r squared, well, we established in an earlier video that 1 over 4 pi epsilon naught is really just kind of an expanded out form of Coulomb's constant, K. So if we get it in that form, it kind of makes sense that the electric field should match up the way it does there. So pretty cool. We derived Coulomb's law. Next, we're going back to that infinite line of charge from the earlier slide. Here we've got an infinite line of charge with a charge density positive lambda coulombs per meter. Now again, charge density there kind of harkens back to the days of doing center of mass and moment of inertia and stuff, where it's really just some amount of stuff per unit length in this case. So here, our goal again is to determine the electric field strength E at a distance r away from the line. So that's just out there to the surface. Now again, a good place to start is really just with Gauss's law, because this gives you a place to start with what variables you should be solving for. Now, we've already kind of let the cat out of the bag with this one, that a cylinder is probably the best course of action for a line of charge like this. That's mostly because the line can be thought of as like a slight wire, and wires are roughly cylindrical shapes. Also, this is an infinite line of charge, so it really just goes out infinitely in two directions. And because of that, well, really here, we don't really see the end of it. So there's really no need to worry about encapsulating whatever the ends of this line are doing. So in that case, since we're going to use a cylindrical Gaussian surface, we're going to need to pick an arbitrary length L for that cylinder. So we'll just call that L. And as such, the area of the cylinder that we make here is going to be 2 pi r L plus pi r squared plus pi r squared. The 2 pi r L accounts for the side of the cylinder, and then these 2 pi r squared terms account for the caps or the ends of our cylinder. Now it's worth noting that we can actually eliminate some things here. If we think about how the electric field lines are radiating outwards, kind of radially from the wire, well, that means that the electric field lines at the very edges right here, where the caps are technically parallel to those circular surfaces. Because of that, we can say that those field lines are parallel, not perpendicular to the caps, and so the flux through those surfaces is going to be 0. Therefore, we can go ahead and safely eliminate both of these pi r squared caps. We're going to assume that no electric field lines are really passing through those surfaces. All right, so then that knocks out pretty much our area requirement. So now we just need to figure out how much charge is enclosed within this arbitrary cylinder. To do that, well, we're gonna kind of employ techniques similar to what we've done in the past with density here. We can say that density, linear charge density at least, is some measure of charge per unit length, as kind of hinted by the units here. Because of that, well, some amount of charge would equate to the density times however much length we have. So then if our cylinder is enclosing some amount of length of charge like this, then the charge enclosed must be our density that we're given times the length of the cylinder that we have. And so that's going to be the expression for our charge enclosed, lambda times L. So we've got both of the things that we really need here. Everything else is either something we're solving for or is a constant. So we can go ahead and start plugging in. So if we plug in our area and our charge enclosed formulas, we'll end up with E times 2 pi r L equals lambda L divided by epsilon naught. Now here, there is a certified Spelunky alert because there's an L on both terms of this equation. So we can knock out that arbitrary L that we picked that might have been making you a little uncomfortable because again, that's something that, it should kind of technically matter. Now in this case, it doesn't. And so at that point, we just need to rearrange and solve for E, which in this case, the electric field at any point, at any distance r away from an infinite line of charge like this is going to be lambda, its density, divided by 2 pi r times epsilon naught, the permittivity of free space. So that is a general formula that you can use for any line of charge, so long as the ends of the wire don't really matter. Pretty cool. All right, so we're going to do one more, and it's a slightly weirder one, but very similar in process to the infinite line of charge here. So this third example is going to be an infinite sheet of charge. And this is our first actual two-dimensional shape. The other two have been either a point or like just a one-dimensional line. Now here, an infinite sheet of charge has a charge density positive sigma. Again, sigma is the just density for a two-dimensional thing. And that's going to be coulombs per meter squared. So our goal here is to determine the electric field strength E produced on either side of this sheet. Because note now, electric field can come out of either side. So again, we're going to start with a statement of Gauss's law. And we'll just say we're going to assume that we're going to have to find the surface and probably the amount of charge enclosed within whatever surface we create here. Now in the picture, there's kind of a suggestion to use a cylinder as your Gaussian surface to like enclose the charge there. But really, for a sheet of charge, you can actually use pretty much any Gaussian surface for this shape, and you'll see why here in a second. But just since it's matching the picture, we'll go ahead and try a cylinder that's passing through the sheet on both sides, and we'll see what happens. So again, the surface area of a cylinder is 2 pi r L plus pi r squared plus pi r squared. And here, again, we should try and eliminate any sides that we know that the flux is going to be 0 for. Here, if you note the picture, the electric field lines are going to be passing out kind of perpendicular to the surface of this sheet right here. Now, the other thing that's passing out perpendicular to the sheet is the side of the cylinder in this case. Now, that side then is going to be parallel to these electric field lines. And because of that, the flux is going to be 0 for the sides of the cylinder, meaning the electric field lines are really going to have any noticeable flux through the caps of the cylinder in this case. Oh, how the turntables. So in that case, we can go ahead and eliminate the 2 pi r L, and that means our total area for our cylinder in this case is going to be 2 pi r squared. Now, the next thing we need is the total charge enclosed, and we're going to do kind of a similar thing to what we've done in the past here. Because kind of the cross-sectional area, like on the sheet of charge itself, is a circle, well, if our density is described by some amount of charge per unit area, then we really just need to rearrange that to solve for Q enclosed by saying it's going to be our density, sigma times A. Now the area enclosing that region of charge right there is a circle. So for the area, we'll plug in pi r squared, and then that expression there will be what we use to describe the charge enclosed by this cylinder. Finally, we have our charge enclosed, we have our area, so now we can go ahead and plug stuff into Gauss's law and see what we get for electric field. So for electric field, we'll go ahead and plug our stuff in. We're going to have electric field times 2 pi r squared for our area equals sigma pi r squared for the charge enclosed divided by epsilon naught. Now here again, we have a really nice Spelunky occur with both of the pi r squareds, basically both of the areas. This is why I mentioned that any Gaussian surface really works here. You could technically just plug in area and just keep it as area, and it will still technically cancel out in the end, meaning that R really doesn't matter here. It's completely independent of that. So if we rearrange, then we get this very simple formula for the electric field produced by this infinite sheet of charge. It's the density of charge on the sheet divided by 2 times the permittivity of free space, which is a constant. So this technically means that infinite sheets generate uniform electric fields that really don't vary at all with distance. It's kind of hard to picture that, but again, think of this infinite sheet of charge as just like this ever ongoing floor of charge that just goes on forever. You can't see the end of it on either side. And so really it's just a ton of charge that's all kind of piling up along the vertical, and it largely leads to just this uniform upward or downward field due to that sheet. Again, it's a little hard to picture here, but where this especially becomes useful is on extremely small scales where, you know, a normal sized table to us is pretty much an infinite sheet of charge for something as small as like an electron. And that's where we're able to make these sorts of approximations. So that's just 3 examples. There are many more ways to apply this, but they all pretty much follow the exact same procedure. So if you can get comfortable with the rhythm of finding the surface area, finding the charge enclosed, and then putting all that together in this simplified Gauss's law, you'll find that you can make quick work of this maybe once scary looking formula. So I hope this video helped. I hope that you can practice this a little bit more and get more used to it. And if you can, then this is a big part of electricity and magnetism that you've just gotten out of the way. So that's about it for this video. Thank you for watching, and I will catch you on the next one. Peace.